today we are going to explain some illustrations based on moment of inertia, and finally we will do the exercises. Four identical rods are given, each having mass m and length l, and they make a square frame in xy plane. We have to calculate the moment of inertia along the x-axis and that along the y-axis and also along the z-axis. Let's consider this figure. Let us consider this axis as y-axis and this axis as x-axis. Each rod have got mass m and length l. So the length of this rod will be l, and again that of this rod will also be l. From the figure it is clear that it is symmetric along x-axis as well as y-axis. So the moment of inertia along the x-axis as well as along the y-axis will be same, or you can easily say Ix will be equal to Iy using symmetry. Now calculating the moment of inertia of the rods along x-axis. Let's name it as Ix. Coming to the figure, the moment of inertia of the first rod, let's consider it as first rod, it has second rod, it has third rod, and it has fourth rod. For the first rod, the moment of inertia will be 0. For second and fourth, it will be 1 upon 3 ml square, and for the third rod, it will be ml square. So we can easily say the moment of inertia will be equal to the sum of 0 plus 2 multiplied by 1 upon 3 ml square plus ml square, or you can say it is equal to 2 by 3 ml square plus ml square, which will give the value 5 upon 3 ml square. This is the moment of inertia along the x-axis. Again, the moment of inertia along the y-axis is equal to the moment of inertia along the x-axis using symmetric relationship. So the moment of inertia along y-axis will also be equal to 5 upon 3 ml square. Now considering the moment of inertia along z-axis. The moment of inertia along the z-axis can be calculated by using perpendicular axis theorem, or using perpendicular axis theorem we can say the moment of inertia along z-axis will be equal to the sum of moment of inertia along x-axis and y-axis. As we know that the moment of inertia along x-axis is equal to moment of inertia along y-axis, so we can say it is double the moment of inertia along x-axis, or it will be equal to 10 upon 3 ml square. Now let's see the second illustration. According to the question, a rod of length L is given, which is placed along the x-axis with one of its end at the origin. The second thing which is given is the mass is not constant, it increases with length by the relation dm upon dx is equal to lambda x. We have to calculate the moment of inertia of this rod along the y-axis, and secondly the moment of inertia along the centroidal axis, that is the axis passing through the center and perpendicular to its plane. Let us consider the figure firstly. The rod is given, and let us consider this is the y-axis and this is the x-axis. The length of the rod is given to be L. According to the definition of moment of inertia for uniform distribution of masses, we can say the moment of inertia of this given rod taken as I naught to be equal to integration of x square dm, and the limits of integration will be from 0 to L, where dm is the elementary mass taken, considered, and x is the distance of the elementary mass from the y-axis. Now firstly let's consider dm. So dm will be equal to lambda x dx. So we can say I naught will be equal to x cube lambda dx, or we can say lambda is taken to be common, integration of x cube dx from the limits 0 to L have to be done. It will be equal to lambda x4 upon 4, and the limits of integration are 0 to L. So I naught, or the moment of inertia along y-axis, can be written as equal to 1 upon 4 lambda L to the power 4. Now coming to part B of the question. From the figure we can say the center will lie on this point O, and we have to calculate the moment of inertia along this axis. We can easily see from the figure that the given axis is parallel to the axis passing through the y-axis. Thus we can say, applying perpendicular axis theorem, I naught can be written as IC plus MD square, where I naught is the moment of inertia along the y-axis, IC is the moment of inertia along the centroidal axis, M is the mass of the rod, and D is the distance of the rod from the centroidal axis, or the distance between the centroidal axis and the y-axis. We can see IC will be equal to I naught minus MD square. Firstly, we have to calculate the total mass or the complete mass of the rod. We have been given dm upon dx is given to be lambda x, or we can say dm to be equal to lambda x dx. So m will be equal to integration of dm, and the limit will be 0 to L. We can say it is equal to lambda L square upon 2. Now again, we have to calculate D firstly. D is the distance of center of mass from the y-axis. In order to calculate D, the position of center of mass is to be calculated from the given axis. According to the formula of center of mass, we can say the center of mass will be equal to x dm integration 0 to L upon integration of dm 0 to L. As already calculated, the value of dm will be lambda x dx. The integrand limit of integration will be 0 to L, and again dm will be equal to lambda x dx 0 to L. Calculating the above, the value of d, or the center of mass from the axis of rotation, comes out to be equal to 2 upon 3 L. Now, since we have firstly calculated the value of the mass of the body and finally the value of center of mass from the axis of rotation, thus putting the value in the perpendicular axis theorem, we can say IC will be equal to I naught minus MD square. The value of I naught is calculated to be lambda L to the power 4 upon 4 minus the mass is calculated to be lambda L square upon 2. D is calculated to be 2 upon 3 L. Thus the moment of inertia along the centroidal axis comes out to be equal to 1 upon 36 lambda L to the power 4 on calculation. Let's consider one more illustration. In this given illustration, two semicircular rings have been given. Each ring have mass m and radius r, and they are arranged so as to form a sine curve. We have to calculate the moment of inertia along the x-axis. Now, in order to solve this problem, we can rearrange the rod to form a complete ring. Let's see the figure. The rods can be rearranged as shown in figure. They can be taken as a complete ring having radius r, and this can be done without altering the moment of inertia. Now this becomes a circular ring of radius capital R and mass 2m.